Welcome back to Physics with Mr. McQuarrie. Today we're going to be talking about graphing, specifically how to interpret graphs for scientific meaning and identifying key components of graphs. Graphs might be nice to let you know things like this. Like, for example, in 2019, there are going to be more Lego people than there are real people, which for some people is awesome. Like Emmett here from the Lego Movie, but for the rest of us, not so great. We have two key learning targets today: identifying the components of graphs and interpreting their meaning. Case in point, Governor Andy Beshear from Kentucky in his 1918 Spanish flu graph behind him. He has Philadelphia and St. Louis, and right away you can draw conclusions about the states of those cities during the last pandemic. Why do we graph? Well, on the left, look at that data table. On the right, look at those bar graphs. Which one would you prefer to use? Probably the bar graph, right? It's pretty, it's easier to read, and you can draw conclusions about it pretty quickly. There might be less serious ways to use these too, like determine what kind of hot dog condiments most people like. Or maybe you want to know the interest of fidget spinners over the course of history on Google searches. You can see everything peaked in about the end of school 2017. If I remember correctly, that serves my memory about right. Or with, to say you're a baseball fan, you want to know the win probability for your team. And you can see here, the Reds have over a 90% chance of losing, which, if you saw that game, seemed kind of low. All right. Now, we use data tables to help us set up our graphs. Data tables look like this. They organize data, and that's about it. Okay. It's hard to draw conclusions by just looking at the data tables, but they're nice to get your data down. Line graphs are a little easier to read. Okay. You can compare two sets of data. Sometimes it can be time, distance, height, and age, like this case, but two sets of data. All right. On the x-axis, you have the independent variable, and on the y-axis, you have the dependent variable. The independent variable is the thing that determines the dependent variable. In this case, for example, it's the grade level that determines height, not the other way around. Your height is dependent upon your grade level. Just because you're tall doesn't mean we automatically promote you to high school. Just because you're short doesn't mean you're always stuck in elementary school. All right, so that helps you identify independent and dependent variables. Scatter plots are another way we can plot our data. All right, you have your data points, those are those blue dots, and then you draw a line of best fit. A line of best fit is something you may have not encountered before. Basically, it's a line that tells the story of your data points. It's a line that goes through most of your data points, or at least close to them. It does not connect the dots. If you want to connect the dots, you can go get a coloring book. But in physics, we don't have coloring books. All right, we draw lines of best fit. Now we have parts of a graph. Here's our example again of students by grade level. You can see that a title is included that tells the story of what's going on. You can also see that we have axis labels as well to let us know what is on the x-axis and what is on the y-axis. Now let's go over some graphing basics. A helpful acronym to remember everything we need to create a graph is DETAILS. Kind of like in basketball or football when someone says defense, we have DETAILS. DETAILS. Feel free to use that in your next student section. The D in details is that data needs to cover at least half the graph. This graph on the left here has a lot of wasted space, and it's hard to see what's going on. On the right, it's much easier to see what's going on And we can calculate things like y-intercept and slope with that. T stands for title. You need a title to let your readers know what is going on in your graph. If you want to use the old standby of independent variable versus dependent variable, you can do that. Or you might get a little more creative. For example, over here, you could say the effect of sleep on quiz scores. A stands for axis labels. We need to label our axis so we know what's going on in your graph. It serves a lot of the same purpose as your title, but this case, it's with your x and y axis. I for interval marks. You need consistent spacing, and you need to start at 0. All right. In this case over here, this is an example where they didn't do that. You can see that they're spaced out a little weird here in the beginning on the x-axis. The y-axis looks decent, but in both cases, they decided to not start at 0. That can be misleading. L stands for labeling your units. How are you measuring quiz scores? How are you measuring sleep? Is it in minutes, hours, days, or if you're Rip Van Winkle, years? We need to know those things. Example, if you're going to measure things in height, are they in centimeters or meters? That can tell, that's a huge difference right there. And finally, S for scale. Always go by an even scale. On the x-axis, our scale is by ones. On the y-axis, it's in 25. Okay? You don't want to have things like logarithmic graphs. They're a little more difficult to read because they don't go by the same scale. If you're having trouble with labeling, specifically identifying where do I put my independent variable and my dependent variable on graph, you can remember the phrase dry mix. All right. Independent, I, x-axis, x. That's where we get mix from. Dependent, D, y-axis, y, dry mix. For some students, this can be a helpful device to help them remember. Finally, we're going to move on from not just what are good parts of a graph, but how to read the graphs we've been given. Now we're going to change gears here a little bit. Instead of just identifying what are good parts of a graph or what makes up an excellent graph, we're going to interpret some of the mathematical components of this graph, namely slope, intercept, and what they mean in terms of the word problem we're dealing with. Let's refamiliarize ourselves with a few terms from algebra. Slope, base of the rate at which stuff happens. It's the amount of this per that. Slope is the change in y divided by the change in x, aka the rise over the run. I like to tell my students finding slope is easy and fun. Just remember rise over run. The y-intercept, it's like the original. All right. When x equals 0, this is what you got. AKA, it's where your line crosses your y-axis. Your x-intercept is the opposite. It's where it crosses the x-axis. All right. So when your dependent variable, which we'll get to later, or y is equal to 0, what is x? And then we have an equation where we combine all these elements. Y, your dependent variable, is equal to the slope of your line times your independent variable, aka x, plus your y-intercept. And those are good for questions like predict what will happen when this happens. Like when x is equal to this number, what will y be? That's your math translation. Or when this is equal to 0, what happens? So that equation helps us find things about that current situation really easily. All right. Like this, for example, if we're given the following line, we can piece together y equals mx plus b. Okay. We can find the slope, which is the rise over the run. In this case, we rise 1 pound for every 2 miles. So our slope is 1 pound per 2 miles. We can also find the y-intercept, the part of where the graph actually intersects with the y-axis, or the line intersects with the y-axis on the graph. So that's where we get the following equation, y equals 1/2 x plus 2. All right, so let's do an example like this. We have a scatter plot. We try to draw our line of best fit. We want to find the equation of that line of best fit. Looks kind of like this. All right, first things first, we need to find the slope. All right, the slope is easy and fun, rise over run. We rose 2 and went over 1. All right, so our slope is 2. For our y-intercept, we can see clearly that the line intersects the y-axis at 3. So our equation looks like y equals 2x plus 3. Another instance here. This time, though, it looks like our graph is going down. So we're going to have a negative slope. We start out here at 14. We go down 2, and we go over 2. Be mindful of the intervals that your graph is using. In this case, each little tick mark here is 1. But on this axis, each one is 2. So in this case, we are going down 2, and we're going over 2. Over and over and over again. So our slope is -2 divided by 2, or -1. Our y-intercept is where the line intersects the y-axis. In this case, it is 14. So our equation, if we fill in everything we're given, is y equals -x plus 14. Now's the part about science. We want to interpret what these things are telling us. What does the slope mean in the context of this problem? What does the y-intercept mean in the context of this problem? Let's take Sarah's Saturday stroll. We can clearly see the y-intercept. It's 5. But what does that mean? We can clearly see the slope. We can calculate that slope as going up 1 over 2. So the slope is 1/2. But what does that mean? Well, plug that in our equation. Let's answer some questions about Sarah's Saturday stroll. So what is Sarah's original position? Original position means that she's starting out. And if she's starting out, time must equal 0. Time is equal to 0 tells us at that point she's at position 5 miles. How fast is Sarah moving? Well, fast is kind of like miles per hour, meters per second, feet per second, something per something. So if we were to take maybe the slope of this line, we'd end up with miles per hour. That's the speed. That tells us how fast she's going. How fast is she going? Well, what's her slope? You go up 1 and over 2. So her slope, or her speed, is 1/2 mile per hour. How far has Sarah traveled after 3 hours? Well, we go to our 3 hours, go up here. How far has Sarah gone? Well, it appears that she has gone roughly 6.5 miles. That doesn't make any sense here. Why is it 1.5? Well, the question isn't asking her position, it's asking how far she's traveled. So she is at 6.5 now, but she started out at 5. Think about that. There's a difference between how far she's traveled and her position. So you gotta be really careful to read these problems carefully. How far would Sarah have traveled after 10 hours? Well, this is a case where it might be nice to look back at our equation. Okay? Our equation says that she goes 1/2 mile every hour. So after 10 hours, we could plug 10 in for x. She would have gone roughly 5 miles. And what is Sarah's position after 10 hours? So now we're asking for the position, not how far she's traveled. We go back to our equation. It's still y equals 1/2 x plus 5. We still plug in 10 for x, but this time we're going to include the 5, that head start that she got. So she actually went 5 plus 5, or 10. Let's look at Preston's pool. All right, Preston's filling up his pool. We want to know how fast that pool is filling up. All right, how fast something is sounds a lot like slope, because in this case we get gallons per hour. That shows us the flow rate. So let's look at what the slope is. For every 500 gallons, 1 hour elapses. To me, that sounds like a slope, 500 gallons per hour. How much water did the pool start with? Well, at time t equals 0, or hour is equal to 0, we see that there is nothing in the pool. So how long will it take to fill up the pool if it is 5,000 gallons? Well, that's where we're going to use our equation again. All right. We have a slope of 500, or m. We have a y-intercept of 0 for b. But in this case, we're not given time, or x. We're given our dependent variable, volume. So we're going to substitute 5,000 in for our volume. So here's our equation. We plug in our 5,000. We solve for x. It becomes an algebra problem. It takes roughly 10 hours for Preston to fill up his pool. So, all in all, today's lecture, you've not only identified components of graphs, but you've also got a little bit of practice of applying those to real-world situations. Till next time, see ya.